A maximum power point tracker is a device which maximizes the power generated from photovoltaic cells. It can also be recognized as an electronic circuit that links solar arrays and the battery. Maximum power point trackers do this by finding the maximum power point located near the drop-off of an IV curve. The maximum power point tracker is necessary because it matches relatively low voltage of a solar array and the high voltage of the battery. Motivation for a maximum power point tracker is because solar arrays are able to produce large amounts of electrical energy, but this isn't necessarily able to be used by the load. When the maximum power point of an array is located, it allows for the array's optimum voltage and current to be transformed by a DC-DC converter to better suit a determined load. There are two general methods to track the maximum power point: indirect and direct methods. Indirect methods take the measurement of either the open circuit voltage or short circuit current and estimate the maximum power point to be a fixed fraction of this value, around 0.8. This is less reactive to environmental and non-ideal factors. Direct methods take two partition measurements of the cell's performance and compares them to find a better value. It repeats this process for increasing voltages until the maximum power point is found. The per tube and observe method uses this sampling method for power and is the most effective for solar cars due to its relatively simplistic and realistic real-world performance. System design would consist of the solar cells, the maximum power point tracker, and the battery. One end of the voltage current sensing modules connects to the input of the DC-DC boost converter, while the other is connected to the microcontroller, which would utilize an analog to digital converter to measure the input voltage and the current of the DC-DC boost converter.
The converter works by chaining the DC output from the solar panel into a duty cycle desired by the MPPT. The voltage is then amplified and changed back into direct current via a boost converter. The output voltage is related to the duty cycle as shown. Choosing the correct boost converter is critical as it must have high efficiency for the expected voltage and current input and output ranges. There are two methods to sense the voltage and current input from the solar cells: voltage sensing and resistive current sensing. Voltage sensing requires a microcontroller to sense the voltage. However, the microcontroller can only handle small voltages, so a voltage divider is required to bring the voltage down by utilizing just two series resistors. An alternative method to using a voltage divider can be achieved through resistive current sensing, which is done by inserting a very low ohm resistor into the circuit. We can then measure the voltage across the resistor and therefore calculate the current using Ohm's law. The addition of the resistors does cause a small power loss, but it is less than the loss from a voltage divider would generate. A microcontroller is designed to track the maximum power point with a processor memory and programmable peripherals. Two light-dependent resistors will measure the intensity of light with the help of a microcontroller. By comparing different light intensities, the solar panel can rotate and absorb the best light intensity, and the microcontroller can therefore track and adjust the maximum power point. Laying out all the components of a PCB will create the MPPT controller, and to integrate all the components effectively, they need to have some basic features. The PCB board needs to be compact, preferably the size of a credit card, and lightweight, less than 100 grams, producing MPPTs for solar cars, Ariel, Aurora, and dilithium power systems. These systems are all very comparable. However, based on three main factors: efficiency, weight, and tracking ability, it was found that the dilithium power system's MPPT is the most desirable.